Swayam Prabha. Digital India. Educated India.
Hello and welcome to the lecture number 14 of the course Robot Motion Planning. In the last class, we looked at the potential field method, and we'll continue with that discussion today. Then we'll look at path planning using a navigation function, and then from there we'll move on to the potential field method in 3D. So if you remember, whatever we are talking about in the potential field method till now is basically limited to 2D cases. That means you have a flat ground in which you have obstacles, and the robot basically avoids the obstacles and goes to the goal point. Okay, so from there we'll continue with this discussion and then move on to navigation function, and then we'll look at potential field in 3D. Okay, very briefly revising what we had done in the last class regarding the potential field method. So in the potential field method, we basically assign potentials, okay, attractive and repulsive potentials, to the goal, the robot, and the obstacle. So if we have a robot here and we have an obstacle here and my goal is given here, so we basically assign attractive and repulsive potentials to guide the robot avoiding obstacles to reach the goal. So for example, if I assign plus charges here and I also assign a plus charge to the robot, then obviously, so this is my plus charge here, so the robot is going to be repelled by the obstacle. And we give a minus charge to the goal, so the robot essentially will move like this, will avoid the obstacles, and then will go to the goal. Okay, so basically we avoid an attractive potential and a repulsive potential, and at every point in the vector field the robot is subjected to a force which is the gradient of the potential. Okay, so the gradient of the potential, we say the gradient of the potential is a force which guides the robots towards the goal away from an obstacle. Force, or we can also say it's a velocity of the robot. Okay, so now we have to assign attractive potential. That means we have to define a function, attractive potential function, and define also a repulsive potential function. So what we saw in the last class is that the attractive potential can be a conical potential, which is equal to u, which is equal to zeta into the distance between the present position of the robot and the goal position. So as shown here, if qxy is the present position of the robot and qxgyg is the goal position of the robot, then d is the distance between the goal and the present position of the robot. And if you write this as d, then the distance is given by x minus xg squared plus y minus yg squared, square root of that. And when I differentiate this function u with respect to x, I get this term, and if I differentiate this with respect to y, partial differentiation with respect to y, I get this term. So du by dx, or del u by del x, and del u by del y are given by these two functions. And from here is what we get the gradient as zeta by d into q minus q goal. Now the disadvantage of this is that when the robot reaches the goal, then what would happen, this d will become equal to 0. So this gradient will become undefined. Okay, so that is the problem here. Now to avoid that problem, what we do is we can use a quadratic potential. The quadratic potential essentially, we write it in the form half zeta d squared, where d is again the distance between the present position and the goal position of the robot. Now when I take the grad of this, then what we do get is equal to zeta into q minus q goal. Exactly in the same way, distance is equal to x minus xg squared plus y minus yg squared, and we take the partial differentiation derivative of u with respect to x and then with respect to y. So I get this term and this term. So my grad is equal to zeta into q minus q goal. So when the robot reaches the goal point, what would happen is this distance will become equal to 0 and the grad will become 0. Okay, but it does not become undefined. So what we can do is that we can use both of them, the conical and the quadratic potential functions, using each of them at a particular distance. For example, we define a distance q star, and when the robot is at, let's say, at point q, and the distance is d, which is the distance between the goal and the present position, d is less than equal to q star, then we say we are going to use the conical function. Okay, and when the robot is d greater than q star, then we say we are going to use the quadratic function. We can define the values q and q star, okay, as an whatever we require. Now, something you note here before I proceed, that there is a constant that is used, which is zeta. Okay, so that means the force acting on the robot, which is the grad of the potential, will be directly proportional to zeta. So how do you get zeta? That is a question that might come to your mind. So zeta is a constant, so different numerical values can be assigned. For example, a high value of zeta will give you a high force. Okay, a low value of zeta will give you a low force. Okay, so now zeta depends on the person who is writing the program, and we'll see how zeta is also found. Now, so this is the conical potential and the quadratic potential functions that are used depending on where is d. D is less than q star, or d is greater than equal to q star. Okay, sorry. Okay, so that is basically what we call is the effective distance. Okay, so let me call this a particular distance, or okay. Now, so much for the attractive potential. Now we need to define the repulsive potential. The repulsive potential U repulsive is defined as half eta into 1 by d minus 1 by q star. So where q star is the effective distance. Okay, so q star is the distance where the repulsive force becomes effective. Force x. Okay, now why q star is put? Essentially because if you have obstacle here, let's call this an obstacle, and you have the robot at this point, and you have the goal at this point. Okay, now as we said that we have plus plus here, and we also have a plus, a minus here, and a plus here. So what would happen is at every point in the vector field, if the repulsive force is also acting on the robot, then the path is going to become longer. That is just common sense, right? So for example, if we are at this position here, the shortest distance would be a straight line. But if the robot is here and the repulsive force is also acting at that point, then it will tend to move the robot like this. Whereas the robot could have simply gone like this, like this, like this, and then gone like that. Okay? So we basically put a distance where the repulsive force starts acting. So we put some kind of a barrier and say that my q star is only here. So this is my q star, which is the distance from the obstacle. And d is the distance from the obstacle. This is distance from obstacle. So if I take the grad of this, what I get is eta into 1 by q star minus 1 by d, and the whole thing in brackets, into 1 by d squared. So please note that there is a d squared there. So it basically means that d is the distance between the robot and the obstacle. So when the robot comes into this distance d, so what it basically means, okay, this is my distance d. What it basically means, the force is going to increase very, very quickly because it's a d squared. Okay, and at the surface of the obstacle, when the obstacle just goes and hits that, d becomes 0. So this becomes infinity now. Okay, so what you can see is that the way the repulsive potential has been formulated, essentially to ensure that when the robot comes right on the obstacle, the force becomes infinity. So that cannot happen. So the robot will get pushed away. Okay, so this is basically to show that the effective distance q star actually controls when the repulsive force will become effective on the robot. Okay, now again we have a constant here. This is an eta constant. So again, if eta is high, the repulsive force will be high. If eta is low, then the repulsive force will be low. So we have two constants, zeta and eta, and we have to find values of zeta and eta, right? So now let's look at how to use the gradient descent method. So we take the potential, the effective force acting on the robot, so total force on robot is equal to attractive plus repulsive force. So and I take I use the gradient descent. That means I minimize so it's a minimization problem. So basically what it means is that I'm minimizing the potential energy. So if you can imagine if there is a ball that it has a potential energy mgh, then when the ball comes down, this decreases, right? Now the problem with this potential field method is that there is a possibility that the robot can get caught in what we call a local minima. Suppose we have a global minima here, but the robot can get caught into local minimas, and this is a problem which is faced by the potential field method. So what we do here is we use the force acting on the robot, okay, and then drive the robot in a direction which reduces the potential by using the negative gradient descent, and then we have to be careful that it doesn't get caught in a local minima. Now this is basically a pictorial view of how the whole thing works. So we have an obstacle which is given here, and we have a goal which is there, and the robot is somewhere here. So suppose I say my zone of influence is somewhere here. Okay, so this what we are talking about, this Q star, this is also called the zone of influence. Okay, so only in that distance the effective force is going to start working, not otherwise. So suppose I have my zone of influence here, which is my Q star, and the robot is coming towards the goal. Okay, now it is moving almost in a straight line towards the goal because that is the shortest path. Okay. Only when it enters the zone of influence, then the repulsive force starts pushing the robot away. Okay, not before that. So from here, the robot is getting pushed away. It goes like this, like this, like this, and goes to the goal. Okay, so there are two constants that we are seeing. One is an eta, and there is a zeta and eta. Two constants are there. Okay, so how do we find optimal values of this? Now, eta is here, and zeta and eta. Okay. Now, how do you get their values? There is no, so when we use the word optimal values, then what do we mean by optimal here? So optimal could mean, first of all, whether it has reached the goal, whether it's a global minima there, that is one. Now, the optimal values could be with respect to some cost function. With respect to some cost function. Okay. Now, what is this cost function? Or what are we trying to minimize? So we're trying to minimize, for example, the path length. Obviously, we want the robot to reach at the fastest. We can say minimum energy. We can minimize energy of the system. We can minimize distance from obstacle. So these all could be cost functions that we are trying to minimize when we're using the potential field method. So what we basically do, you can write a program, okay, which varies eta and zeta, okay, for put different numerical values, okay, compute path length, or maybe energy, or maybe distance from obstacle, and then see which is the minimum case. So which is the minimum zeta and minimum eta. You can use standard optimization like genetic algorithms. Okay, so genetic algorithms can vary eta and zeta, and basically we can have a cost function which is going to be minimized. So minimize cost function, which can be the path length. Okay, so what this fundamentally does, if I were to show it to you pictorially here, suppose we start saying zeta is equal to 10 and eta is equal to 1. Now something to remember is that the attractive has to be greater than the repulsive. Otherwise the robot may never reach the goal. If the repulsive force is more, then it will tend to push the robot really away and it may never reach the goal. So attractive is normally higher than repulsive, and that is the reason I put eta equal to 10 and zeta equal to 10 and eta equal to 1. And suppose we are getting this path for eta is equal to 10 and is equal to 1. Now suppose I increase eta, suppose eta is equal to 2, then what do you expect? As eta is equal to 5, for example. What do you expect? You expect that the robot will come like this, and it will go further away now, like that. Okay, why? Because this has become higher now. Okay. Now if I make it even higher, then what will happen is, suppose I make it 10 and 10 and let me make this 8, just for example, some other color. Let's say this is 8 now. What will happen is it will go like this. As soon as it's in the zone of influence, it will get pushed out. Okay. So what you're seeing is here is that the path lengths are different. Okay, are different, right? So now we can say that put a value of eta and zeta such that we get the best path length. Okay, the shortest path. Best path length would mean the shortest path length. Now, for example, I say the path length which will give me how do you define the path length, or which is the shortest path length? Suppose you're writing a program and you want to minimize the path length. Okay, minimize this. So what is the shortest path length? The shortest path length is a straight line between the goal and the right. So if I come back here and I say that I'm joining this with a straight line, now that is my shortest length path. Right. So the path which is the closest to this, so this I can take this difference and say that okay, that is the deviation from path. Let me call that a deviation E, and I minimize that. So whichever path gives me the minimum E, let's say I divide this into 20 points. Okay, and for each of those points I actually find what is the deviation from this straight line, and then I do the sigma of that and say that this is my total deviation, and that is how I'm going to minimize my path length. Okay, so you can write a program in C language or any other language, MATLAB, and actually find the values of eta and zeta. Okay. So this is sometimes we call tuning, and you have to tune this because there is no other way of finding that out. Now it can be with respect to path length, it can be with respect to energy. When we go to 3D cases, you will see that in 3D, when the robot starts climbing up, then there is the energy consumption goes up. Okay, so in 3D applications like in autonomous vehicles and unmanned aerial vehicles, then it's a question of energy. Which one takes less energy? Okay, and so in this case, it need not be that it's a straight line is the best path, whereas you need a path that is going to give you the minimum energy. Okay. When we come to 3D applications, we'll look at this today. Okay, so you can have different, you can have a combination path length plus energy plus distance from obstacle. So these are all cost functions which can be used. But what I'm trying to emphasize here is that there is nothing like what is an optimal value of this. What is eta? It depends on the values you have put. And if I increase it, for example, I make zeta equal to 100. Okay, eta equal to 10. What will happen? It will get pulled faster. So every point in the vector field will be subjected to a force which is much higher. Okay, so if this was my force F1, this is my force F2, and F2 is greater than F1. So it will move faster in terms of energy, in terms of velocity. Okay, so far we looked at mobile robots. Now in the last class we were looking at serial manipulators also. Now in the case of serial manipulators, we need to find what is the relationship between the end forces acting on the end effector and that and the effect of it on the joints. So for example, what I'm trying to say here is that we have a manipulator, two-link manipulator. Okay. So there is a force acting here. Let's say there is a force F acting there. So Fx, Fy, Fz. Okay, and there is a torque, and this is causing a torque which is tau there. What is the relation between tau and F? Why? Because we can convert all the forces acting at different points on the manipulator. For example, there is an obstacle here. So let me draw an obstacle here. There's an obstacle, and I want to go from this point to this point. This is my goal. So what I can do is this force which is acting on this robot is because of this there is some force acting. So in each of these points, these are forces acting. So these repulsive forces are forcing the manipulator away, whereas the attractive force is pulling the end effector towards the goal point. Okay, and again it's a potential field method. So I'm going to assign forces, potentials, take the gradient, and then find the forces acting on these points. Maybe point here, point here, point here, and then forces, find the effect of the forces on the torques, and then sum all the torques. Then go to my C space. So essentially, what we are trying to do is we are finding the relation between forces and torque acting at a joint. Now, if there is a force F which is acting at the end effector here, let us say this force produces a small deflection dx. Okay. Now, correspondingly from virtual work, this force is equivalent to a torque at the joint which has a small deflection d theta. Okay. And from virtual work, principle of virtual work, we can say that F transpose into dx is equal to tau transpose into d theta. Now we also know that d theta is equal to j into dx, where this is my joint velocity and this is my end effector velocity. Okay, so this we do know. So now I can take this and I can take d theta and put it here. Okay. So what I get from that equation, f transpose into dx is equal to tau transpose into j into dx. So I have dx on both sides, so I can cut this and I can cut that, they cancel each other. Now if I take the transpose of both sides, then what we do get is tau is equal to j transpose f. Now please note that this j is in last frame. Okay, it is not in the first frame. That means the force is acting on the last frame. So this gives me a relationship between the end effector force and the joint torques. Now, if there is a end effector force acting, or there are different forces acting on the different links, then we can convert them into the joint torques and I can sum them up. Okay, and then say that these are the forces acting on my manipulator in C space. Okay, so please note that this is done in Cartesian space. Okay, so what I mean is there is a force acting which can be Fx, Fy, Fz. Now, what is the use of this? The use of this is essentially we can use this principle when there are multiple forces acting on an object. Say this is a mobile robot. So let's say this is a mobile robot. It has 4 wheels. Okay, and this is my global frame, x-axis, y-axis. And with respect to this, the coordinate of this point is ax, ay. Okay, and the local frame is here, x dash, y dash. Okay, so now what I can say is that suppose there's an obstacle here. This obstacle is applying a force Fx, Fy at this point. Let's call this point P. Okay, now this obstacle could be applying a force on other points also. So this is my another force, let's say P dashed. Okay, so it could be applying some other force on that point P1 or P dashed. Okay. What I can do is I can take all these forces Fx, Fy acting at point P, convert to torque, take the force acting at P1 or P dashed, convert that to torque and add them all up. And once we add them all up, then I can say that in C space, where the robot is a point, all these moments are acting on the robot now. Okay, so how do I do that? I basically find the kinematic relationship. So this is my kinematic relation or geometric relation, where because these two are rotated, the local frame is rotated by an angle theta, then x, the coordinate of the point P1, the coordinate of the point P is given by x. In the x direction, it is x plus ax cos theta minus ay sin theta, where ax and ay are the coordinates of the point P in the local frame. Okay. Then if I take the derivative of this with respect to dx, dy and theta, then what I get is this is my J matrix. Okay, so first I take the derivative with respect to x, then I take the derivative with respect to y, okay, and then I take the derivative with respect to theta. So what we do get is my Jacobian matrix J, and then I will use my relationship which we just saw, tau is equal to J transpose F. This is my F and that's my tau. Okay, and what we do get is I get the moment which is acting, which is the last column here, this one, on the point P. Similarly, I can find the moment which is acting on the point P1, P dash, P2, P3, whichever point, and then I can sum them up and say that this is the force, this is the moment acting on the robot. Okay, which will tend to rotate the robot and take it in some other direction because of this obstacle. Okay, so what we apply this for is by choosing different points onto the robot and seeing what forces are acting on those points. Say for example, if you have a very large robot like this and we have a sharp obstacle. Now suppose I take the force acting here is P1 at point P1 and the force acting there is P2. Okay. Then what we can do is I can convert these forces at P1 and P2 into a moment which is acting onto this on the robot and move it accordingly in C space. Now please note that suppose I say there is only P1, okay, and the robot will tend to rotate like this. What will happen is this part may go and hit the obstacle now. Okay, so I have to choose enough number of points, choose enough points so that the robot doesn't hit the obstacle, robot avoids obstacle. Okay, So you have to choose. Again, choosing the points is up to you. I can choose this point and I can choose this point. This may not be enough because this might hit. Okay, so the force is acting there, force is acting here. But what can happen is it can hit this point now. Okay, so it might be a good idea to choose many points here and see what are the forces acting on all of them. Convert them by this equation, sum them up, and then see what is the force acting on the robot and move it accordingly in C space. Now, exactly the same thing we do in the case of serial manipulators. So in the case of serial manipulators, we know that the gradient vectors of the potentials are forces. So the basic idea is to define forces in the workspace. Okay, that means if this is a manipulator, okay, I choose these points, 1 point here, 1 point here, 1 point here, 1 point here, and say these are the forces acting because of an obstacle. Now suppose I want to go from here to here. What I will do is I will assign potentials here. Let's say I say if this is my, this is plus, this is minus, this is minus. Okay. So the obstacle will tend to push the robot away, and the forces will be acting at all these points that we have chosen. Now you have to choose those points. End effector is 1 point, maybe the joint centers are another point, and see what are the forces acting on those joints. Convert them into C space forces, okay, and then go to C space and then do the planning. Okay. So forces acting in Cartesian space of the robot are converted to C space and then added. Then the robot moves in the resultant direction. Okay. Now, so it's very important here that we pick points in the manipulator that are attracted to the goal and those that are repelled from the obstacle. For example, in this particular case, suppose my goal is here, okay, and my initial point is there, start point is here. Then I have to choose, because the end effector has to go to the goal. So if I say this is my plus and that's my minus, okay, then this is plus, plus, plus. Now, it is not enough to say the end effector should go to this point, okay, because in the process these links can go and hit the obstacle. So I have to also choose points on the links now. Okay, so you have to choose points on the links. So goal has to be attractive. Now choose points on links to avoid it hitting the obstacle. End effector towards goal. Okay, and the end effector has to be attracted towards the goal. Now each of these links is an obstacle to itself. Please note that. Okay. So for example, if there is a robot like this and there is a link like this, then this is going, it can go and hit that. Okay, so a link is also an obstacle. So if I put plus and plus, they will not hit each other. Suppose I put a plus here and a goal point is minus. This will get attracted here. Okay, but this and this, there's an obstacle here. So this and this will get, the link 1 and link 2 will start repelling each other also. Okay, because it can happen the link can also hit itself. So one link is an obstacle for the other link. So this is how we basically do path planning for serial manipulators. Now this is an example I had shown earlier when we talked about C space for serial manipulators. So on the left hand side we have the workspace or Cartesian space. Okay, so this is my Cartesian space where we have a 2-link manipulator and these are obstacles. Now from here we go to the C space, so this is my C space, and we are going to do the planning between in the C space. Okay, say for example the distance between the here, suppose I want the manipulator to go from this point to this point, just for example. So I want the manipulator to go from in the bottom position, it is say theta 1 is equal to 0 degrees, and this somewhere here. So theta 2 is about 300 degrees, let's say. So theta 1 is 0 degrees and this is 300 degrees. So it is somewhere up there. Okay, and I want it to go to that point where theta 1 is equal to about 5 degrees. Somewhere here is about 10 degrees. That's it. It's here. And your theta 2, let's say the manipulator is like this. Theta 2 is equal to 0 degrees. So theta 2 is 0. Where is 0? It's here. So here. So this is my position 1. This is my position 2. So from position 1 to position 2, okay, I want to go. Okay, so how do I go? Now I have marked my positions. This is C space now. So what we do is I can assign potentials at different points on the manipulator. I assign a potential onto the end effector point there, and I assign potentials here and here. Okay, and then I assign values, attractive and repulsive potentials. This is my goal point. Okay, so that's my goal. So this has to be attractive, and these are obstacles, so they has to be repulsive. So I see the forces acting at those points, end effector and the links. Use the equation tau is equal to J transpose F, and then sum all the torques, and then come to the C space. And now when I'm in the C space, then suppose this is my plus plus plus. Okay, this is the obstacle, right? And this is also plus plus. This is also plus 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 plus. Okay, these are plus plus. So the robot is going to move from here like this and come to the goal point. Okay, depending on the torques which are acting in a particular direction, which is moving the robot away. Okay, so this is essentially to show how planning is done in C space for a serial arm robot. Now we have seen that this potential field method suffers from some problems. Okay, one problem is this question of local minima. Now this local minima happens when the attractive force becomes equal to the repulsive force. Okay, that means the net force acting on the robot is equal to 0. So net force on robot is equal to 0. Now, for example, in the left-hand side case, we are seeing here, when the robot is coming in like this and comes here, so the force that is pulling it away and the force that is attracting it, the net force becomes equal to 0 there. Okay, so the robot just stops there. Now, it would appear that it has reached the goal because the robot has stopped, but it has not reached the goal. Similarly, on the right-hand side, if there are two obstacles placed like this, then what can happen is the robot can go like this and come here. So the force in this direction, force in that direction cancel each other, and sigma F is equal to 0 again. Okay. So the problems is that the final position of the robot is not guaranteed to be a global minima. The other thing that happens very often is that if you have motion in this kind of boundaries, it can start doing like this. It can start chattering. Okay. So this is one problem, that the position of the robot is not guaranteed to be a global minima. Now, how do we ensure that the final position will be a global minima? That is the question here. Okay, how can we ensure that it is not a local minima, but it's a global minima? So if you can have a function which does not have local minima, or the local minima near the goal, okay, then there is a high chance that it will go to the goal only. Okay, and such functions are called navigation functions. So we have seen that the other problems that are there are bug algorithms. The earliest bug algorithms, they are complete, but they work only in 2D. Okay, potential field method suffers from problem of local minima. Now, wavefront planners don't have the local minima problem, but require large storage. So these are the problems that are there. So is it possible to construct a potential function with the minima at goal and whose domain of attraction includes the entire subset of C space and is connected to the goal? Now, in that case, all the local minimas would be near to the goal. And if they're connected to the goal, then it will go to the goal ultimately, right? So such functions are called navigation functions. So a function is called a navigation function if it is smooth. Okay, why does it have to be smooth? Because you want to take the derivative and it must be continuous. Okay, that is why it has to be smooth. Next, it has a local minima at Q goal, is uniformly maximal on the boundary of free space, and is Morse. Okay, so one such function is this one, which we call the sphere world. Now, in the sphere world, you can imagine this to be a sphere. Okay, so this is a sphere. It's spherical. And these are obstacles. These are also spherical. Okay, like ball. Now, this is my goal point, and this is the robot start point. Okay. Now, there are local minimas in there, so there is a chance the robot will get stuck somewhere. Okay. So we have to define a function such that the local minima will tend to move towards the goal. Okay, so that ultimately it goes to the goal. So how do we define such a function? Say, for example, a function would again mean an attractive potential and a repulsive potential. Right? So the repulsive potential here is given this way. So this is my repulsive potential for the obstacles, where R0 is the radius of the sphere. So R0 radius of sphere. So this is my R0. Okay. Then Ri is the radius of obstacle. Okay. So R1, R2, R3, R4. Now beta is the repulsive potential, which is equal to minus d squared into q into r naught squared. Okay, and this is the repulsive potential for the sphere, the larger sphere, the outer one. And for an obstacle, it is d squared minus ri squared. Okay, what is d? D is the distance. D is equal to distance from obstacle. Okay, so d is the distance from the obstacle. Now, when it comes to the boundary of the outer sphere, what will happen? This one will become 0. And if it comes to the boundary of an obstacle, inside obstacle, it will also again become 0, because d squared will become equal to r squared. Okay. Now, so now the total repulsive potential is equal to the sigma, or the sum of beta I. Okay, this is the total repulsive potential acting on the robot now. Now, what is the attractive potential? The attractive potential we are defining like this: gamma k is equal to the d. D is the distance between the robot and the goal, raised to the power 2k. So depending on k, we can put 1, 2, 3, 4. Okay, this attractive force is going to change. Okay, now we know that if I take the ratio of this gamma by beta, now this is equal to 0 at goal. Okay, why? Because your gamma will become 0 at goal, because it's the distance between the present position of the robot and the goal. So at goal it is 0. Now this goes to infinity, otherwise at this surface of the obstacle. So this by beta, so gamma by beta is equal to infinity at obstacle boundaries. So if I can define a function like this, now we are defining the function this way, a cost function maybe, which is equal to d squared by d to the power 2k plus beta raised to the power 1 by k. Okay, so I'm defining my navigation function for sphere field this way. Okay, and then seeing for different values of k, how does it behave? Means how is the contour lines moving? Where is the minima? Are the minima constant, or they're moving towards the obstacle? So these are obstacles as written here. So these are obstacles. So obstacle 1, 2, 3, 4. Okay, so there's an obstacle here also. Now you can see that these are local minima. Okay, these are the contour lines of the potential function. So these are the local minima there now. That means if the robot is moving from here, it can go there and get stuck there. Okay, because these are all local minima here. Okay, now this is for value k equal to 3, k equal to 4, k is equal to 6. Now what you're seeing is that if you look at the contour lines are moving such that the local minima are getting pushed in that direction. We said that the local minima near goal or at goal. Because now if you can ensure that, now k is equal to 8, k is equal to 10, k is equal to 12. What we see is that at k is equal to 8, please note the local minima, these points. So these are moving towards the goal. So they're all coming in this direction. If you can see that they're all moving in this here. So k is equal to 12, everything has been squeezed here, and the goal is here, right? So we have brought the local minima near the goal now, which means that when the robot is moving, what is going to happen? The robot is going to move like this, has come here, so it has to only go there now. So the chance of getting stuck in some other local minima somewhere else is not there. Okay, so such functions are basically called navigation functions. And for each problem, you have to write your different navigation function. It is not like there is a standard navigation function. Okay, so for different problems, depending on the problem, we have to define our navigation function also. So this was an example of our navigation function. Now let's look at a few simulations of the potential field function, a few examples of robots which are avoiding obstacles, and so this is an okay, so here we have a robot which is represented by this circle. This is the start point, that is my start point, that's my goal point. Now these are walls. You can consider this to be the top view of a room. Okay, so these are all boundary walls. Okay, these are all boundary walls, and these are all walls where the robot cannot hit. So we are going to assign attractive potential to the goal, repulsive potential to the walls, and the robot also has a potential such that the goal attracts it. So the robot will be attracted towards the goal and it will go and reach the goal. So let's have a look here. So you can see that the robot has started off. I'll just go back a little bit. Okay, so the robot has started from there. It is moving towards the goal. Okay, so it goes almost in a straight line towards the goal. It comes near the wall, it gets reflected or deflected, and then it crosses the wall and then goes to the goal. Now we can place the robot at different positions in this wall, in this room, and then so let us see if we are positioning the robot in different positions. Here the robot is positioned here. So let me rub this out. So the robot, in this particular case, the robot is positioned here. The goal is still the same point. Okay. Now simply by assigning potentials, what we are doing is the robot is moving. You can see from the narrow passage is going out towards the goal and reaches the goal. Now we choose another location. Again, you can see the robot has moved. Now we can choose another location which is on top there. It is avoiding the top wall coming and then reaching the goal. Now at every point, if you note very carefully, it is getting repelled if there is an obstacle there. Okay, so this is the way the potential field method works, by assigning different potentials to the robot and to the goal point and making it move. Okay, so this is another case where the robot is there, it has come and it's reached the goal. Okay. Now this is another example that we are coming to. This I just showed you. So let us move to the second one. Now this is an example of a mobile manipulator system. Okay, so this is basically an example of a mobile manipulator system. Now this mobile manipulator system basically means that there is a mobile robot. So let me draw a mobile robot here. Okay, so mobile robot has wheels, okay, and there is a manipulator on top. Let's say there are some degrees of freedom and there is a mobile robot on top. Okay, this is called a mobile manipulator system. Okay, so there is a mobile robot plus a manipulator. Now the objective here is that the mobile manipulator starts off from there. Okay, now it is there and the goal point is here. Okay, at that point. Now this is showing the top view. Okay, the right side view is showing you the close-up. This is the zoom view. So you can see the robot there. Okay, now the manipulator on top is folded initially. So what it does basically is that the mobile robot reaches near goal, okay, and then the manipulator opens up to position the arm as desired. Suppose I want to say that I want the manipulator arm to be positioned like this, okay, having some alpha, beta, gamma. So what it does is, first the mobile robot avoids obstacles, goes to near the goal, then the manipulator arm opens up and then it aligns itself against the whatever is the desired position. So let's see, please note carefully, the top view you can see the small dot is moving, okay, and on the right side view what you can see is that the mobile robot is moving, avoiding obstacles. So it has come very near obstacles, as you can see on the right side figure. It just avoids the obstacle. There's another obstacle it avoids. Using this potential field method only, using attractive and repulsive potentials. Now the red dot is the goal position, so it comes, note carefully, so it is coming very near the red dot, which is the goal position. So it comes near the red dot. Now this is a zoomed up view. So it has come near the goal position, that has come near the goal position. And the desired manipulator configuration is this. So the end effector should be pointing in this direction like that. Okay, that is desired. So now the robot has come very near the desired goal position. Now it opens the end effector. The manipulator opens up, mobile robot moves back, and it goes and aligns itself. See how it is aligned itself along the direction as desired. Okay, so this was an example of a mobile manipulator system where we are using a potential field function on the manipulator and the robot, but initially the manipulator is fixed, it's not moving. Only when it comes near the goal position, then the manipulator is enabled. Okay, So these are interesting applications for mobile manipulator systems. Now, let us move on now to the next part where we're talking about applications in 3D. So whatever we were talking about till now are all applications in 2D. Okay, 2D means flat ground with obstacles. Okay, so how did we approach the problem in 2D? We basically said that we can divide it into free space and obstacle space. Okay. The robot cannot go into the obstacle space. It is free to go anywhere in the free space. That is how we approach the problem. But suppose now you have 3D case. Now this is 3D. Okay, this is like a lunar Martian surface or a lunar rover, or maybe the roads and 3D terrain in outdoors. Now in this case, it is difficult to classify terrain as free space and obstacle space. Why? Say for example, I have a lunar vehicle like this, a lunar rover or a space rover like this. Now it has a special mechanism which is called the rocker bogie mechanism, which can enable it to climb. Okay, so this robot can go on flat surface. It can also climb. Okay, because it has a rocker bogie, which is this mechanism here. Okay, so this enables the robot to climb very easily. Now because this robot can climb, now when we are looking down on this surface here, is this an obstacle or this is not an obstacle? How do you decide? Because if the robot can climb on top of it and go, then it's not an obstacle, right? Whereas in the 2D case, the robots were not climbing obstacles, they were just avoiding obstacles. Here we are saying the robot can not only climb but it can also avoid. Okay, so how do you define what is free space, what is obstacle space? So you cannot actually. No, you can, in the sense that suppose we say that, let's look at the right side picture. Suppose you say that this is a very steep gradient there. Okay, so I'm talking about a gradient now. There's a very steep gradient there. Now the robot obviously cannot climb that. It can become unstable, it can topple over. Now that is an obstacle. Let's say a very high gradient is an obstacle. Okay, so that I can classify and say this is an obstacle. But what about a small gradient like that? The robot can go over that. Okay, so what we can do is we can say very high gradients is an obstacle, it should not go there, but low gradients it can go there. So basically what we are seeing is that in 3D we have to worry about the gradient now, which we did not do in the 2D case. Okay, now what is the gradient? If I take a grid like this, then each of these grids will have a normal to that, and the angles this normal vector makes with respect to the 3 axes, I can define the gradient that way. Okay, so in the previous case it was flat ground and all the vectors were like this. Okay, so there was no problem. But now, because the grid is having different inclinations, each of the grids has a gradient now. And now we have to worry about the gradient. Now the gradient also plays a very important part in the energy consumed. Okay, because if it has to go higher, if it has to climb, it will take more energy. Okay, because it's increasing the potential, mgh. If it is going down a slope, it's going to take less energy. Okay, so what we can do when we are going from 2D to 3D, we can worry about the gradient. So in the potential field function, we can add the gradient, also gradient function. Let's call it a gradient function, okay, which will take care of the gradient it is going to. So basically I can say the robot should not climb something. Okay, it should go down because it saves energy as far as the energy is considered. The other thing is, how do we figure out wheel contact? Now to find the wheel contact, what we do here is, there is no sensor which can give you wheel contact because you don't know when it is made. And especially if you're doing a simulation, then how do you know where is wheel contact? So basically what we do is, we use any kind of optimization or geometrical procedure in which we say that if this is my terrain and that is my wheel, then this contact point on the wheel, let's call it WP, and that is W terrain, WT. Then W terrain minus W wheel is equal to 0. I can use this as a cost function. So geometrically I can find points. So suppose this is my x, y, z. Okay, this is my x, y, and z. This is my x-axis, y-axis, and z-axis. Right. So at every point of x, y, z there, I can say the z is such that Wt minus Wp is equal to 0. Now if Wp is below Wt, that means it has gone inside the ground. and if WP is in air, then the distance is non-zero, right? So exactly when contact has been made at every XY, so this is unique for an XY, right? So for every XY on the terrain, there will be a Z where contact has been made. So using geometrical method or by using some kind of optimization which minimizes this, you can very easily find contact points for every XY. Now, in order to minimize energy, okay, what we can do is we can say that our potential function now has another component which is my gradient, depends on the gradient now. So as before, we have an attractive force, we have a repulsive force. Okay, so attractive force will attract towards the goal. This will repel from the obstacle. Okay, the gradient is the one that is proportional to the gradient of the grid there now. So if I minimize it, it will not climb, try and climb, it will come down. Okay. Now we can also have a tangential force. So this is tangential force basically for traps or minima problem. So if the robot gets trapped, you can use a tangential force which will take it away from the trap. Okay. So this is the potential field function. This is one way in which we can operate in 3D now. So this is an algorithm extension from 2D to 3D. I've added this one to take it to 3D now. Okay, so this is 3D, this part is 2D. Okay. Now I have to write my attractive force and repulsive force. Now attractive force can be written this way. Okay, so exactly similar to what we had done in the last case, where d is the Euclidean distance between the goal and q, and I can have my conical function. Okay, so I can have a conical function or I can have a quadratic function. Okay, then take its gradient. For the repulsive, I can have exactly the same. So this is the repulsive gradient, 1 by d minus 1 by, this is the effective distance. Okay, and it is 1 by d squared. So it is exactly the same what we were using in the 2D case. Okay. Now the tangential force depends on dq, where q is the, so the tangential force can depend on case of trap. Okay, so depending on if there is a trap, where the robot is not able to go forward but has not reached the goal, then a tangential force can be used. Okay, for example, there is an obstacle like this. Okay. The robot has come here, it has got caught. So at this point, a tangential force F10 can be used to push the robot away and push it in this direction. Okay. Now, what about the gradient force? Now, how we define the gradient force is, let me go back to this figure. It's easier to explain here. So I said that there is an x-axis, y-axis, and a z-axis. Okay, and this is also called my roll pitch yaw. Roll pitch yaw axis. So this is my roll axis. This is my pitch axis, and this is my yaw axis. Okay, so what we can do is, at a particular location, at this particular point, if the robot or the rover is pointing in some other direction, suppose it's pointing in that direction, okay, then I can compute the corresponding roll pitch yaw between the two configurations. Okay, so if I take the top view, let me take the top view. There's something like this. Okay, so the robot is like this. It has 6 wheels. Okay, this is my XY. So for the same XY, please note the XY is same. Okay, what can happen is that the roll pitch yaw, if it is pointing this side or it is pointing this side, okay, the roll pitch yaw can be different. Okay, roll pitch yaw would be different. So it depends on the heading angle. Suppose it's pointing this side or it's pointing this side. The XY is the same. Why? Because it is 3D terrain now. So in different positions on XY, depending on which side it is facing, this roll pitch yaw angles are going to be different. So what is it that we want? We want that the rover should not climb too much. Okay, or it should not become, this is climbing. One side has gone up, this is one wheel. Let's say this is another wheel. This is climbing, right? So it is sideways, it has climbed. Now in the front direction also, if it climbs, this can be a front direction climb, where it is 3 wheels here. It is climbing like that. Again, the roll pitch yaw angle is there. Okay. So what we can do is we see that this climbing and energy would depend on the roll pitch yaw angles now. Okay, especially pitch and roll. Okay. So for different yaw angles, this is a different yaw, this is a different yaw, which is a bearing. It would have different roll and different pitches. Okay. So what we are seeing here is that what we do when the rover is standing at a particular XY, okay, for different phi z, which is the yaw angle. We compute what is the sum of the roll and the pitch. So this is the roll plus this is the pitch, and the gradient force that is being used is exponential of this function. So it is e raised to grad into cos phi z. And what is grad equal to? Grad is equal to the sum of the roll and the pitch angles. Roll plus pitch. Okay. So when it is on flat ground, what will happen? The roll and the pitch angles will be 0 because it's on flat ground, right? So it doesn't matter. But the moment it starts climbing, the roll and the pitch angles will start going up. Okay, so if it's going up or it's going down. So if it is going down like this, for example, the robot is going down like this. So this is my pitch angle, right? So this is my, which is my pitch angle. So this is the pitch angle. So that's the pitch angle. So on the side direction, if it is going down like that, okay, this is my robot. What will happen is this pitch angle is lower now. Okay, whereas if it's climbing, the pitch angle is higher. So you can see that directly this gives us an indicator of whether it's climbing, whether one side is low, one side is high. Now depending on that, if I minimize the function, then what I'll get, so I'm minimizing everything, right? So the attractive force, repulsive force, tangential force, and grad force. Okay. So again, you see that there are constants W1, W2, W3, and W4. So we can use different programs, optimization programs, and genetic algorithm can be one of them, where we basically have random values we can put for this W1, W2, W3, W4, and we can evaluate a cost function. The cost function can be energy. Okay, it can be wheel velocities, omega squared, where is wheel velocities. Okay. So we can evaluate this or we can evaluate this and say which one gives us the least value. Okay, so optimal weights would means vary W1, W2, W3, W4 and get minimum cost function. So the cost function we had that can be used is length of path into the wheel velocities. But this can be energy also. Energy, total energy of the motors, energy of motors taken by motors. Okay. So if you do that, what we find is that in this kind of terrain, this is the top view, and this is the side view. Okay, sorry. Yeah, so this is the top view, and this is probably an isometric view. So we are comparing between 2D case and 3D case. Okay. So in 2D case, what we see, in 2D case, there is no gradient. Okay, in 2D case, if this is my start, that's my goal. The robot just tends to go like this and go there. Because it's 2D case, it doesn't care about gradients. It doesn't know gradients. But the moment you come to 3D case, what you find is that the robot, this is a 3D case. The robot is avoiding all these high gradients. You can see these are very high gradients. It is avoiding all of that and taking a path which is smoother, almost flat ground. So the energy requirement has come down. And if you look at the values of the W's, W1, W2, W3, W4, you find that in all cases, W1 is the maximum. This is the highest. And W3 was low. And this is also important. This is the second highest. Okay, so this is second highest. That means this shows the importance of gradient forces in case of 3D cases. That means 2D cannot be applied, 2D potential field cannot be applied directly to 3D. Because if you don't include the gradients, the robot will simply find a path which is the shortest path. But that can take very high energy. Okay, because they start climbing all over. So if you include the gradient forces, what happens is that we get very low energy and you get a very safe path. So today we looked at the potential field function in 3D. Okay, so we looked at the potential field function in 3D. In 2D, then we looked at navigation function, then we looked at 3D. Now, something to note is that whatever we have been studying so far, okay, we found a network of paths, we found multiple paths in potential field method. Then we looked at multiple network of paths in, for example, the sampling-based methods, Voronoi diagrams we drew, the visibility graph methods we did. Now we have to answer the question of how do you choose a path now? Okay, which path are you going to take? Okay, how do you decide that? So next thing that we'll look at is what we call basic search. Using basic search, how do you find which is the best path? Okay, so thank you. We'll stop today.